Okay, so now we're going to our next topic. It's about degeneracy of linear programs and the efficiency issue. So these two things are definitely related, and that's the reason that we put them in the same video. Okay, so we mentioned this in the previous week. An LP may be degenerate if multiple bases corresponds to a single basic solution. Okay, so let me first remind you about this definition. So for example, in this example, we have this two inequality linear program. In the standard form, there are in total 4 variables with 2 equality constraints. Okay, so with these 4 variables and 2 constraints, we know for every basis there should be 2 basic variables and 2 non-basic variables. In total, there should be 6 bases. Okay, because I mean there are at most 6 bases because 6 comes from 4 chooses 2. So for this linear program, I mean standard form linear program, we have these candidates of bases. And in this example, they are all bases because all the columns you choose can be linearly independent. And then we see that for the first 3 bases, the bases are different, but the corresponding basic solution is identical. Okay, so that's why we say this linear program is degenerate, because we have this situation. If we map basic feasible solutions with extreme points, we can see that in this figure, this particular point counts for 3 basic feasible solutions. Certainly, this is just 1 point. Okay, so when we give them 3 different labels, they are actually 1 single point. There are only 3 3 extreme points, but they together corresponds to 5 different bases. Okay, so this is a situation with degeneracy. Okay, this is a degenerate linear program, and now we're going to give you some idea about what will be the impact of degeneracy for the efficiency. Okay, so in a degenerate linear program, multiple feasible bases corresponds to the same basic feasible solution. When we run the simplex method, it's possible to move to another basis, but because now they correspond to the same basis, so we may still be at the same basis. The same basic feasible solution. So let me say this again. In the simplex method, each time when we do one iteration, we change one basic variable by one non-basic variable, right? So we change the basis and we move to another basis. But when we do that, now because this another basis may actually correspond to the same basic feasible solution as in the current one. Okay, so it's possible that after one iteration, we are still at the original basic feasible solution. So now it's never guaranteed that in every iteration you will change to another solution. And if that's the case, an iteration may have no improvement at all because you stay at the same point. So let's run the simplex method on this particular example. So when we use the simplex method to solve this problem, things are not very special. So first we do a simple entering and leaving, and then we get to the second tableau. Here again, entering and something new is here. The first row has a ratio which is 3. The second row has a ratio 0. Here, one thing to remind you is that some rows do not participate in the ratio test, right? If the denominator is 0 or negative, that row does not participate in the ratio test. And here is the numerator that is 0. This does not violate the regulation of ratio test. Okay, so for this row, the ratio is 3/1. For this row, the ratio is 0/1. Both are fine, and in this case, this particular row will be having the smallest valid ratio. Okay, so that's why this number 1 is the pivot, and now x4 should leave the basis. But if you really do so, okay, entering, leaving, what's going to happen is now that we will get to the third tableau. Here, certainly we may see that the second row will be identical. Okay, I mean the right hand side of the second row will be identical. There will be some other number that will still be 0. Okay, and in this case it's x2. We try to enter x2. That means we try to make x2 larger than 0, okay? Increase from 0 to some positive numbers. But here we cannot do that because according to the algebra, the first thing you should do is to divide the second row by some other number to make this number 1. But in any case, the right hand side is 0, so you will always have 0 after you do so. Okay? So x2 enters, but its value must be 0. Okay? Its value must be 0. And after we will complete everything, you can see that now the new solution is 3, 0, 0, 0. And the original solution is 3, 0, 0, 0. x4 is basic or x2 is basic does not change the solution. Okay? From here to here, you are still at the same solution. And you spend one more iteration to get rid of this situation, to get out from the particular solution. So it's clear that in the second iteration, from here to here, there is no improvement at all because we are at the same solution. And the basis changes, but the basic feasible solution does not. Okay? x1, x4 is a basis. x1, x2 is another basis, but the basic feasible solution is the same. So now we know with degeneracy, it's possible for a linear program for the simplex method to have no improvement in one iteration. So when the simplex method is used, we may have some iterations having no improvement. And this may happen, okay, if the following things are true. If that's true, the thing may happen. Okay, no improvement may happen, but that does not mean the condition is sufficient. So that may happen when multiple rows win the ratio test at the same time. Okay, so you may go back to the previous slides to check that in the first tableau, the multiple rows win, the two rows both have the same smallest ratio. Okay, and that's why basic variable would become 0 in one basic variables, and that's why in the next iteration, that 0 may win the ratio test. For some very strange instances, the simplex method will need to travel through all the basic feasible solution before it can make a conclusion. Here, making a conclusion means to find an optimal solution or to show that the problem is unbounded. Okay? Some researchers have created some very strange instances to show that the simplex method need to travel through all the extreme points or all the basic feasible solutions. And if that's true, then we know that the simplex method, we call it an exponential time algorithm. Somehow, if you are not familiar with the complexity theory, then that's fine. Here, just keep in mind that it may take a very long time for the simplex method to solve a linear program. Okay? We mentioned to you that given a linear program, the simplex method can definitely solve the linear program. Okay, that's true. Definitely solve means definitely solve it in a finite time. Okay? As long as we are patient enough, we can solve that problem. But for some very strange cases, it's possible that we spend too much time or unacceptable time to solve a linear program. So if that's true, then that means the simplex method is not perfect. But fortunately, for linear program problems, there are polynomial time algorithms, and that means for any linear program, there are algorithms that can guarantee to solve linear programs in acceptable time. Okay? But interestingly, for many practical problems, the simplex method is still faster. Okay? So let me put it in this way. The simplex method is theoretically not so good, but practically for many practical problems, the simplex method is better than many other new methods. Okay, so that's why the simplex method is still widely used in industry, and one is because it's kind of simple. Okay, at least it's easier to than other methods, and also it's practically useful. Okay, so that's why the simplex method is still the most popular in industry in almost all the softwares you use in solving real problems. Regarding the efficiency, let's say some more. When we use the simplex method to solve a problem, the number of functional constraints has a larger impact on the computation time. Some advanced results have shown that when we use the simplex method, roughly the number of iterations we need is proportional to the number of functional constraints. And in each iteration, roughly we need m square operations to calculate everything we need. Okay, so in total, the computation time for the simplex method to solve a linear program is proportional to the cube of the number of functional constraints. Okay, so when you formulate linear programs, typically, I'm not saying always, but typically, if you can have fewer constraints, okay, fewer relevant constraints, then typically that's good. That can save you some time in solving linear programs, okay? Because the number of constraints plays a role in the calculation time. On the other hand, the number of variables typically is not very important in determining the calculation time. Then one simple intuition is that in every iteration, we need to calculate, this should be capital B, not very important. Okay? In each iteration, we need to calculate this, right? AB inverse B, and this gives us the basic variable. We know all the non-basic variables are zero, but this guy need to be calculated by ourselves. And AB, this matrix, is m by m. It has nothing to do with n, the number of variables. Okay, so certainly this explanation is just very rough, but I just want to give you some intuition. So the conclusion is that the number of constraints is important, but the number of variables is not. So if you can have an equivalent formulation which has more variable, but with less or fewer constraints, then typically that may be better. Some other things, the sparsity of the coefficient matrix A is also important. Here, sparse means in this matrix there are a lot of zeros, and the practical problems typically have sparse coefficient matrices. Okay, we don't want to spend too much time on this issue. I just want to say that the structure of your problem definitely have some impact on the efficiency of the simplex method or other methods. Okay, so in one aspect, we just need to use the simplex method to solve problems. That's good. In another aspect, if we are really interested in enhancing the efficiency of the current methods, then we certainly need to know more or investigate more about the problem in structures. Okay, so this is just one very simple example. If you know that in your A matrix there are a lot of zeros, how would you utilize this property to save you time? For example, to save some times in calculating AB inverse to save you some time in doing Tableau iterations. That are some possible directions to go. So if you are interested in this, if you want to see more information, see chapters 5 and 7, which will not be covered in this course. So what we're mentioning here about efficiency, you just need to know those very basic concepts. We will not ask you to calculate anything that is specific related to efficiency, okay? But you need to just get some ideas about the concept. One last thing is that there's one terrible thing that is even worse than running for a long time. Is that at a degenerate basic feasible solution, the simplex method may actually enter an infinite loop, which we call it cycling. What does that mean? If I am currently at basis 1, and this is a degenerate solution, that means there are multiple bases corresponding to the same basic feasible solution. Then it's possible that in one iteration I move to another equivalent basis, and then another equivalent basis, and then go back to myself again. That's possible, and examples has been created to show that this is possible. If that's the case, then we cannot guarantee that the simplex method can solve any problem, right? Because if we enter an infinite loop, then for a long time, there is no conclusion generated. And then we cannot say the simplex method may solve any problem. Why? This contradicts to our previous claim. And here I'm going to tell you why. The thing is that we need a good way of selecting entering and leaving variables. For example, suppose I select entering variable with the most significant reduced cost. Then this rule is not so good because cycling may occur. Most significant means for maximization problem, I choose the smallest or the most negative reduced cost. For minimization problem, I choose the largest reduced cost. Okay? Suppose I use that rule, I can show you that there are some examples that you will eventually end up with cycling. So there are at least two ways to avoid cycling. One is that when you have multiple candidates, you just randomize your selection. Okay? If that's the case, because you are not going on a deterministic route, then definitely sometime later you will exit this loop. Okay? So randomization is a way. Another way is to apply an anti-cycling variable selection rule. That means some rule that is somewhat better and guarantee that an infinite loop can be avoided. For example, one anti-cycling rule is the smallest index rule. Here is the description. Suppose we use the smallest index rule, we can guarantee to solve any linear program in finite steps. You will never see an infinite loop. So suppose this is a minimization problem. For non-basic variables that we may enter, pick the one with the smallest index. Here index just means the thing that you use to order those variables. For example, all those variables if are called x1, x2, x3, blah blah up to xn, then index is just those 1, 2, 3, 4, 5, 6, 7. So if x2 and x5 both have positive reduced cost, you will select x2 and ignore the values of their reduced cost. Okay? Because x2 has the smaller index than x5. For basic variables, that's the same thing. If there are multiple rows having the smallest valid ratio, then you will pick the one with the smallest index again. So for example, if x5 and x10, they both have the smallest valid ratio, their denominators are positive and their ratio are smallest, then you will pick x5 because the index is smaller. So blend has shown that if we use the smallest index rule, definitely we will end up with a conclusion in a finite time. Certainly, it does not guarantee the least number of iterations to the optimal solution, but in fact, no variable selection rule can guarantee to be the most efficient. Okay, if you can find one, then that will be a huge improvement in this field, and that will be a very good contribution to the society. Okay, many people believe that's not possible. So, conclusion: the simplex and the smallest index rule guarantees no cycling. It does not guarantee the most efficient, but it guarantees a definite conclusion. Okay, so that's something related to efficiency. We just mentioned it very briefly, and I hope you just get a brief idea. Then that's enough. Okay, thank you.